In this video, one will be able to understand the theoretical calculations, the simulation or the verification of theoretical calculations over PSpice for resonant frequency, two half-power frequencies, bandwidth for given RLC circuit. So I am Mohan BS, working as assistant professor in Department of EEE, SJBIT. So before going to the experiment, let us quickly understand few basic concepts related to resonance. So here let us see how inductive reactance and capacitive reactance behave when we change frequency. On x-axis we have frequency and x-axis, y-axis we have reactance. So given that XL is equal to 2 pi FL, so as F and XL they are directly proportional, their circuit becomes linear. Similarly here F is inversely proportional, so we'll have a hyperbolic curve. So when these two frequencies meet, when these two reactive inductance meet at a point where they collide, forms a resonant frequency. At that resonant frequency we have the circuit behaves as pure resonance. So XC is greater than XL for lesser frequencies, and XC is actually smaller compared to XL for higher frequencies. So this one has to understand how frequency is directly related to XL and XC. Now this is the resonant graph with respect to frequency and your current. So you can see at resonance we can have a maximum curve, a maximum current. At this point we have F0 and we have maximum current. It's been calculated with 3 decimal points, or the RMS value of current. We get two half power frequency. That means at these two particular frequencies the power is being halved. They're named as F1 and F2, and the difference between these two are called as bandwidth. That is F2 minus F1 will give us bandwidth. So let's see the problem. That is to solve for F0, omega naught, Vc, I max. Let's see all one by one. So to find omega naught, F0, then let us find I max. So F0 is given by 1 by 2 pi root LC hertz. We know omega is equal to 1 by 2 pi, 1 by root LC. So substituting the values of LC, and we get the value of F0 as 159, and we get the value of omega naught as 1000 radians per second. So we know by observing this we can correlate V1 as I max into 125. At resonance frequency current is maximum. Let us apply mesh analysis to find the current I max. So assuming the KVL, current in clockwise direction, we can write this as 125 plus 10 I max minus 1.05 V1 into V1. So what is the value of V1? Substitute the value of V1 as I max into 125, and then plus XL into I max minus XC into I max is equal to 15. So this equation, just a normal mesh equation that we have applied. Now at resonance we know XL is equal to XC, thus XL and XC they cancel each other. So we can rewrite the equation and thus calculate the value of current as 4 amperes, approximately 4 amperes. And the value of R, total R, is equal to V by I max, V in by I max, that is 3.75 ohms. Now, so let us see to find VC at omega naught. So we know voltage is given as I into XC. The magnitude of VC is equal to I max into 1 by omega naught into C. Substitute the value of omega naught, substitute the value of current, we get approximately VC as 16 kilovolts. Let us find the two half power frequencies. So we know, let us first find out Q, that is quality factor. Q is equal to omega L by R. So since the value of Q is greater than 1 or greater than 5, we can substitute the values of F1 and F2 as F0 divided by 2 pi L. So here there's a small change. So what one has to do is here, it is substitute as 4 pi, not 2L. It is F0 minus R by 4 pi, and similarly for F1 also as F0 divided by F0 plus R by 4 pi L. So substituting that, you get the value of F1 and F2 as shown here. Since the value of Q is greater than 1, the formulas will change. So I repeat, F1 as F0 minus R by 4 pi L. Similarly F2 as 4.0 plus R by 4 pi L. So subtraction of these two, F2 and F1, F2 minus F1 will give us bandwidth 149.2078. So in PSpice it is A1 minus A2. So the value of F1 and F2, F1 is F0 minus R by 4 pi L, and F2 is equal to F0 plus R by 4 pi L. Substituting these two values, you will get these values F1 and F2. Let's see the connection that must be done. So we need VAC, we need 2R, we need 1L, 1C, 1E, that is the dependent part, and 1 analog ground. Right. So let's So let's get all the paths. Either get recent paths, you can type the part name here, get the elements, place and close R. So place them according to the circuit diagram. We need to. Then once it's done, you can press right click or escape button. Now let us get the inductance. Let us get the dependent element, that is E. The part time that is required for inductance is L. Place it accordingly. And the part time that is required for capacitance is C. Then the part time required for AC supply, that is VAC. Place and close. The last part that is required is the common ground, that is EG&D, that is analog ground. Okay, now we have got all the parts. Let us connect them. The keyboard shortcut is Ctrl W. So the one which is encircled is a dependent element. And the one which is not encircled is your independent. So this is dependent element, you can see, which is encircled. So in rhombus here we have plus and minus. So similarly over there in PSpice in circle we have plus and minus. Okay, so now this is your dependent voltage source, or voltage dependent voltage. So this is your dependent element which is encircled. So positive you can see is connected to inductance, and negative you can see is connected to 10 ohm, that is at R2. Let us do connect as it is, as the given circuit. And then now where is this dependent voltage source? So this voltage source is depending on the voltage of R1, that is 125. So you can see positive is ahead of R1 and negative is at the end of R1. So let us connect as per the circuit that has been considered for solving. So now the connections are done. Now let us value them. So replace the default values to the values that we have considered for calculation. Double click, replace it for 125. Now let us see how do we give the gain as 1.05. So double click on E poly. As a double click, the default value of gain is 1. So in our problem we have gain as 1.05, right? So let us substitute the gain as 1.05. Click on save attribute. Now we have taken the marker. Go to setup analysis, enable DC AC sweep, sorry, not DC AC sweep, and the number of total points you can give more than 10,000, so you can get more accurate values. And then the starting frequency as shown in the lab manual, it should be slightly lesser than your F1, and end frequency should be slightly greater than your F2, sorry. So start frequency lesser than F1, end frequency greater than F2. Then click on OK. Save your file and then simulate to see the output. It takes time because the number of points that it must simulate are more. So you can see the percentage that it has taken to solve. So if the number of points are less, it simulates with very less amount of time. So we have kept the probe for current. So the output that we get here is for current. So now, so you can see on x-axis we have 160 Hertz and y-axis we have 4 amperes as maximum. So click on toggle cursor and then cursor peak. So this is showing at the default value of on x-axis is 158 and the value of y is 125, 256. So as you click, it will show you the value. Let us see the cursor, the peak value of current. So you can see it's showing 159.155 and 4 amperes. So at 4 amperes, the X value is 159.155. That's the resonant frequency. That is shown as first cursor, that is A1. Now let us see for the voltage across capacitance. So for that, what you can do is go to add trace. Voltage across capacitance is VC1. Click on OK. And now we have got the graph for capacitance. You can see on y-axis you have 16K. Now since we have selected I, you can see there a box which has been highlighted over here. So now just click V, the voltage curve that we want across capacitance. So let us delete that current, and now you can see a voltage 159.155, that is x-axis. The cursor peak 159.155, that is the value of x. At resonant frequency we have the voltage as 16,000 volts. Now what we'll do is, now we'll type the code to find voltage across L and C, that is the first node of L1 to the second node of capacitance, that is VL1 colon 1 comma C1 colon 2, that is across L and C. So both together you can see the voltage is being minimum. Okay, so let's see that. So that is the first end of L1, and then we have L and C in series. So L1 L has two ends, that is L1, and this is what we have done here. First point of L1 and second point of C2. First point of L1 and second point of C1, not C2, I'm sorry. So L1 has two ends, L1 and L2, 1 and 2. C1 also has two ends, 1 and 2. So we are seeing the voltage between L and C, that is 1 and C12, right? Yes. So that is what is the formula. Or you can simply keep the voltage probe and then simulate again, or you'll also get the same value. You can see the voltage is minimal here, thus it is negligible. So that is, we have seen here voltage across L and C at resonance is 0, or approximately 0, negligible. Now let us see the resonant frequency. The code for that is SFLE 2.828, that is I max by root 2. So here we have got the first cursor, that is A1, and then again click on cursor search, same code. Now click on again OK. So A1 lands for F2. I repeat, A1 is landing for F2. 159.230 is actually your F2. So now again click on cursor search, or let us say, by mistake you click here. You can again, need not worry, just click on the code again and say OK. It shifts back to 159.230. And you can also see there we have done for F1. So we have right clicked somewhere before 159, and we have typed the same code. It lands at F1. So A2 is actually F1 and A1 is actually F2. I repeat, A2 is actually F1 and A1 is actually F2. And difference of these two is your bandwidth, that is 149.253. So this is how we have to find out F1 and F2 and bandwidth using resonance. Let us see again how do we find the two cutoff frequencies. Go to cursor search, and now we have to search for y-axis. The value is 2.828, that's I max by root 2, that is 4 by root 2 is 2.828. So search SFLE, search in forward direction along y-axis for 2.828. So as I click OK, it lands here directly. So I'll just show you. As I click again here, it lands at the first point of this line is a line for 2.828. It cuts at two different points. So this curve is actually F2, and the first as it touches the curve is F1. So since we want A1 to land here for F2, so I'll just again type the code and say OK. It moves to F2. So you can see this value A1 is at F2. Now I'll right click. I repeat, I'm right clicking. For example, let us say you do a mistake and you left click. So need not worry, the code is same. Just ensure that it is cursor 1. We just click it twice and then right click, or you need not even right click, just say cursor search. If it is at 1, you can just click on 2 and then say OK. By default it lands at F1. So in this way, this is F2, this is F1, and this is our bandwidth. Remember, if you are doing it on a hardware, the circuit must be inspected by lab instructor or faculty before you energize. So thank you for watching the video. So please do subscribe the channel to enhance your knowledge further.